Welcome to DAR Tutors, your trusted source for online and home tuition. Today, we're diving into a crucial concept in statistics for IB Mathematics AIIHL, the variance and standard deviation. By the end of this video, you will be able to, first, calculate the variance and standard deviation for both populations and samples, including data from frequency tables and grouped data. Second, you will understand the difference between population and sample standard deviation. And third, you'll be able to solve complex IB-style problems involving these measures of spread. These skills are essential for interpreting and analyzing data effectively, a cornerstone of the IB AIHL curriculum. Before we introduce variance, let's briefly recap other measures of spread we've already covered. We have the range and the interquartile range. The range is the difference between the maximum and minimum values in a data set. It's easy to calculate, but only tells us about the extreme values and can be heavily affected by outliers. The interquartile range, or IQR, is the difference between the third and first quartiles. The IQR tells us about the spread of the middle 50% of the data. It's more robust to outliers than the range. However, the problem with both the range and the IQR is that they are calculated using only two data values. They do not take into account all the information in the dataset. This means that two very different datasets could have the same range or IQR, masking their true spread. To overcome this, we need a measure of spread that considers every single data value. This leads us to the variance and standard deviation. Our first objective is to define and calculate the variance and standard deviation for an entire population. The population variance, denoted by sigma squared, is a measure of how much the data values in a population deviate, on average, from the population mean, mu. Here's the formula. Let's break it down. We are looking at a data set of n values, x1, x2, up to xn. The term xi minus mu represents the difference between each individual data value and the mean. This is called the deviation from the mean. We square these deviations, xi minus mu squared, to ensure that positive and negative deviations don't cancel out, and also to penalize larger deviations more heavily. The capital sigma, S, tells us to sum up all these squared deviations for every value in the population. Finally, we divide by the total number of values, n, to get the average. So, the variance is essentially the average of the squared distances from the mean. Now, the population standard deviation, denoted by sigma, is simply the square root of the population variance. The standard deviation is preferred as a measure of spread because its units are the same as the original data. If our data is in kilograms, the variance is in kilograms squared, which isn't very intuitive. The standard deviation, sigma, is also in kilograms, making it easier to interpret. The standard deviation measures the degree to which data deviates from the mean. A small standard deviation means the data points are clustered closely around the mean, indicating high consistency. A large standard deviation means the data points are spread out, indicating high variability. Let's work through an example to solidify our understanding of population variance and standard deviation. Consider the dataset 3, 12, 8, 15, 7. This is a small population, so we'll treat it as such. First, we need to calculate the population mean mu. We sum the data values and divide by the total count. 3 plus 12 plus 8 plus 15 plus 7 is 45. Dividing by 5, we get a mean of 9. Now, we need to find the squared deviations. It's helpful to organize this in a table. For each data value, x, we subtract the mean, 9, to find the deviation, x minus mu. Then we square this deviation to get x minus mu squared. Let's fill out our table. For x substant 3, the deviation is 3 minus 9, which is 6. Squared, this is 36. For x sub 12, the deviation is 3, and the squared deviation is 9. We continue this process for all our values. The sum of the squared deviations is 36 plus 9 plus 1 plus 36 plus 4, which equals 86. Notice the sum of the deviations, x minus mu, is 0. This is always true for any dataset. Next, we calculate the population variance. We use our formula. The sum of the squared deviations is 86, and n is 5, so the variance is 86 divided by 5, which is 17.2. Finally, the population standard deviation. We take the square root of the variance. The square root of 17.2 is approximately 4.1. So for this population, the mean is 9, the variance is 17.2, and the standard deviation is about 4.15. Often, we don't have data for an entire population. Instead, we have data from a sample of that population. In this case, we calculate the sample variance and sample standard deviation. The formulae are very similar, but there is one crucial difference. The sample variance, denoted by s squared, is the sum of squared deviations from the sample mean, x bar, divided by n minus 1. Notice the denominator is n minus 1, not n. And the sample standard deviation, denoted by s, is the square root of the sample variance, with the same denominator of n minus 1. So why the change from n to n minus 1? This is to make the sample variance an unbiased estimator of the population variance. If we used n, our sample variance would on average be a little bit too small. Dividing by n minus 1 corrects for this. Think of it this way. To calculate the sample mean, you have n pieces of information. But once you know the sample mean, you've used up 1 degree of freedom. You only need n minus 1 of the data points to calculate the last one given the mean. So, we divide by the actual number of independent pieces of information we have. It's a subtle but very important statistical concept that ensures our sample statistics are good predictors of the population parameters. Now for the IB mathematics, analysis, and approaches. Higher level curriculum. A note on this. While the true statistical distinction exists, for the purposes of the Analysis and Approaches HL course, you are expected to calculate all standard deviations as though they were populations. This means you should always use the formula with the denominator, and unless a question specifically asks for the sample standard deviation. We will follow this convention for all our subsequent examples unless the context demands otherwise. However, it is important to be aware of the difference, as it is a key statistical concept. A very common scenario in statistics involves data presented in a frequency table. Let's consider a dataset where a value x appears f times. The formulae for the population mean and population variance are adapted to include this frequency. The mean is calculated by summing the product of each value and its frequency, then dividing by the total number of data values, n, which is the sum of the frequencies. Similarly, the variance is the sum of the squared deviations, each multiplied by its frequency, all divided by n. Finally, the standard deviation is the square root of the variance. Let's see this in action. Here is a frequency table for the number of pets owned by students in a class. First, let's find the mean number of pets, mu. We calculate mu as the sum of x times f divided by the sum of f. This gives us 22 over 24, which is approximately 0.917 pets. Now for the variance and standard deviation. A table is the best way to keep track of our calculations. The sum of the last column is the sum of x minus mu squared times f, which is approximately 30.96. Now we can find the variance. We divide this sum by the total frequency n, which is 24. This gives us a variance of approximately 1.29. Finally, the standard deviation is the square root of the variance, which is approximately 1.14. Often, data is given in classes or intervals. In these cases, we cannot find the exact standard deviation, but we can make an estimate. The method involves using the mid-interval value, which is the average of the upper and lower bounds of each class. For example, for a class interval of 50 to 59, the mid-interval value, or class center, is 50 plus 59 divided by 2, which is 54.5. We then treat this mid-interval value as if it were the actual data point for all the frequencies within that class. The calculations then proceed exactly as with a frequency table. Here's our grouped data on the length of babies. First, we create a table with mid-interval values. X. For example, for the class 40 to less than 42, the midpoint is 41. Next, we calculate the estimated mean, mu hat, by summing x times f and dividing by the total frequency, which is 30. This gives us an estimated mean of approximately 48.067 centimeters. Now we set up our main calculation table. We calculate the squared deviation for each mid-interval value, multiply it by the frequency, and sum them up. The sum of the x minus mu hat, squared times f column, is approximately 144.93. Finally, we divide this sum by the total frequency, 30, and take the square root to find the estimated standard deviation, which is approximately 2.19 centimeters. This is an estimation, as we are making an assumption that all values within a class interval are at its center. While manual calculation is essential for understanding, in practice, we use graphics calculators. Calculators can quickly provide the mean standard deviation and other statistics for a dataset. A crucial thing to know is what the calculator displays mean. Your calculator will typically provide two standard deviation values. The first is sigma x, which is the population standard deviation dividing by n. The second is Sx, which is the sample standard deviation dividing by n-1. As per the IB analysis and approaches HL convention, you should always use the population standard deviation, sigma x, when solving problems unless specifically told that the data is a sample and to use the sample standard deviation, Sx. Let's demonstrate with an example. Here's a list of 30 ages. Imagine we are asked to find the standard deviation. Since it's not explicitly stated as a sample, we use the population formula. The process is similar on most calculators. You'll go to the Statistics menu, enter your data into a list, L1 or Stat1, and then run a one-variable statistics calculation. The calculator output will look something like this. Notice we have sigma x equals 14.318 and Sx equals 14.563. For an IB analysis and approaches HL question, we would report the population standard deviation, 14.3 years. In this specific problem from the notes, it asks for the sample standard deviation for the analysis and approaches course, so you would report Sx 14.6 years. This highlights the importance of reading the question carefully to know which value to use. Understanding the effect of transformations on data is a powerful analytical tool. Let's investigate what happens to the mean and standard deviation when we perform two basic transformations, adding a constant and multiplying by a constant. Let's start with adding a constant. Suppose we have a data set with a mean mu and standard deviation sigma. What happens if we add a constant k to every data value? The mean is a measure of center. If every value shifts up by k, the center of the data should also shift up by k. So the new mean would be the old mean plus k. This is an intuitive result. What about the standard deviation? The standard deviation measures spread. Adding a constant to every data point does not change the distances between the points. The shape of the distribution remains the same. It just shifts along the axis. Therefore, adding a constant k to every data value does not change the standard deviation. It remains sigma. Now let's consider multiplying by a constant a. Again, let's think intuitively. If you multiply every value by a, the center of the dataset should also be scaled by a. So the new mean would be a times the old mean. Again, a very logical result. What about the standard deviation? If you multiply every value by a, the distances between data points also become a times as large. This means the new standard deviation would be a times the old standard deviation. For variance, which is the standard deviation squared, the new variance would be a squared times the old variance. Let's summarize these rules for a dataset with mean mu and standard deviation sigma. If the new data is formed by a linear transformation xi maps to a xi plus k, the new mean will be a mu plus k, and the new standard deviation will be a times the old standard deviation. We've seen that multiplying by a constant like a scales the standard deviation. But what if we multiply by a negative number? Let's explore this with a small example. Consider the data set 1, 2, 3t. The mean is 2 and the variance is 2 to 3. The standard deviation is the square root of 2 to 3. Now let's multiply each value by 1. The new data set is 1, 2, 3. The new mean is 2. This makes sense. The old mean 2 times 1 is 2. Let's calculate the variance of the new dataset. The new variance, sigma squared y, is found by taking the deviations from the new mean, squaring them, and dividing by 3. This gives us 2 to 3. Notice, the new variance is the same as the old variance. So the new standard deviation is the square root of 2, 3, which is approximately 0.816. This means multiplying by a negative number reverses the order of the values, but it does not change their spread or the distances between them. Distance is a non-negative quantity. Therefore, the transformation rule needs to be adjusted. The new standard deviation is not A times the old standard deviation, but the absolute value of A times the old standard deviation. This ensures that the standard deviation, which must be non-negative, remains non-negative. This is a very important detail. A key concept to be aware of in the IB/AI/HL curriculum is the proof section, which asks you to prove certain statistical identities. One common proof is that the sum of squared deviations can be rewritten. This is sometimes called the computational formula for variance, as it can simplify calculations. Let's start from the left-hand side. The summation notation means we sum xi minus mu squared for every value of I. First, we expand the squared term. Xi minus mu squared is xi squared minus 2 times xi times mu plus mu squared. Next, we use the linearity property of summation. This allows us to break the sum of the difference into the difference of the sums. So we have the sum of xi squared minus the sum of 2 mu xi plus the sum of mu squared. Since 2 and mu are constants with respect to the index I, we can factor them out of the summations. This gives us the sum of xi squared minus 2 mu times the sum of xi plus mu squared times n. We sum mu squared in times, so it becomes n mu squared. Remember the definition of the population mean mu. It's the sum of xi divided by n. Rearranging this, we find that the sum of xi is equal to n mu. Now we can substitute this into our expression. We replace the sum of xi with n mu. This gives us the sum of xi squared minus 2 mu times n mu plus n mu squared. Simplifying the middle term, we get the sum of xi squared minus 2 n mu squared plus n mu squared. The terms involving mu squared combine. This results in the sum of xi squared minus n mu squared, which is exactly the right-hand side of the equation we wanted to prove. This completes the proof. This identity shows that the variance can be calculated using the sum of the original data values squared, and the sum of the original data values, which can be computationally faster, especially without a calculator. Let's apply the identity we just proved to solve a problem that might appear on an IB exam. We are given a data set with 25 values. We know the sum of the squares of these values, and we know the population standard deviation. Our task is to find the mean. We know the population standard deviation, sigma. If we square it, we get the population variance, sigma squared. So the variance is 5.2 squared, which is 27.04. Now let's use the definition of population variance. Sigma squared equals the sum of xi minus mu squared, all divided by n. We can rewrite the numerator using the identity we just proved. Substituting the computational formula into the variance definition gives us this expression. The numerator is the sum of xi squared minus n mu squared, all over n. Now we have an equation with sigma squared, the sum of xi squared, n, and mu. We know all the values except for the mean, mu. We can now solve for it. Let's substitute in the values we have, 27.04 for the variance, 25 and 68.25 for the sum of xi squared, and 25 for n. Multiply both sides by 25. This gives us 676 equals 2568.25 minus 25 mu squared. Now we rearrange the equation to solve for mu squared. We add 25 mu squared to both sides and subtract 676 from both sides. This gives us 25 mu squared equals 1892.25. Divide by 25 to find mu squared, which is 7569. Finally, take the square root to find mu. The square root of 75.69 is exactly 8.7. So the mean of the data set is 8.7. Now let's explore a common type of problem where you must compare the means and standard deviations of 2 or more data sets. We're going to analyze the sprint times of 2 athletic squads, A and B, using their parallel box plots. First, let's estimate the 5-number summary for each squad. For squad A, we can estimate the minimum time to be 11.0 seconds, the first quartile Q1 to be 11.6 seconds, the median to be 11.9 seconds, the third quartile Q3 to be 12.3 seconds, and the maximum time to be 12.7 seconds. For squad B, we estimate the minimum at 11.2, Q1 at 12.0, the median at 12.6, Q3 at 13.0, and the maximum at 13.8 seconds. Now let's compare them. Which squad generally ran faster? To determine who is generally faster, we look at measures of center. Comparing the medians, 11.9 for Squad A is less than 12.6 for Squad B. A lower time means a faster speed. Therefore, Squad A was generally faster. Now, which squad's times are more varied? In other words, which squad has a greater spread of speeds? To compare variability, we can use the interquartile range, or IQR. The IQR for Squad A is Q3 minus Q1, which is approximately 0.7 seconds. For Squad B, the IQR is approximately 1.0 seconds. Since the IQR for Squad B is larger, their times are more varied or have a greater spread. In this problem, we were given box plots, so the IQR was the appropriate measure of spread. If we had the raw data, we would likely calculate and compare standard deviations to comment on consistency, with a lower standard deviation indicating more consistent performance. A final topic, which is more conceptual but crucial for higher-level study and understanding, is the significance of a low standard deviation. Let's consider Pratik, a quality control officer at a biscuit company. He needs to check that each packet of biscuits contains 250 grams. He knows that due to the manufacturing process, the exact weight will vary slightly from packet to packet. Pratik could measure the mean weight of a sample of packets to see if, on average, they are close to 250 grams. This ensures he is meeting the target weight. But this isn't enough. He also needs to check the variability of the weight between packets. For this, he would calculate the standard deviation. What is the significance of finding a low standard deviation? A low standard deviation means that the weights of the packets are clustered very close to the mean. For example, if the mean is 250 Gs and the standard deviation is 1 G, it means most of the packets will weigh between 249 G and 251 G. From a quality control perspective, this is excellent. First, it means consistency. Every customer gets a packet that is very close to the advertised weight. Second, it reduces waste. There are very few packets that are significantly overweight or underweight. If Pratik were to find a high standard deviation, it would indicate a problem in the manufacturing process. He might have a mean of 250 Gs, but with a standard deviation of, say, 10 G, meaning packets could range from 230 G to 270 Gs. This is undesirable. So, a low standard deviation is a direct indicator of quality, consistency, and a well-controlled process. Let's work through an IB-style problem to apply the concepts we've learned. We have a set of 10 integers. We are given the mean is 6 and the population variance is 3.2. Our goal is to find the two missing integers, a and b. This problem requires us to use the properties of both the mean and the variance. First, let's use the definition of the mean. The mean is the sum of all the values divided by the count, n. We know n is 10 and the mean is 6. Let's sum the known integers. 3 plus 9 plus 5 plus 5 plus 6 plus 4 plus 6 plus 8 is 46. Now we set up our equation for the mean. 6 equals 46 plus a plus b, all divided by 10. Multiplying by 10, we get 60 equals 46 plus a plus b. Subtracting 46 from both sides, we find our first equation. A plus b equals 14. Next, we use the variance. We'll use the computational formula for variance because we have the sum of x squared values in our head. The formula for variance is the sum of x squared divided by n minus mu squared. Let's find the sum of the squares of the known integers. This sum is 272, so the sum of all squared values is 272 plus a squared plus b squared. Substituting the values into the variance formula, we get 3.2 equals 272 plus a squared plus b squared, all divided by 10 minus 6 squared. Now we solve this for a squared plus b squared. 6 squared is 36. So 3.2 plus 36 equals 39.2. Multiplying by 10, we get 392 equals 272 plus a squared plus b squared. Subtracting 272, we get our second equation. A squared plus b squared equals 120. We now have a system of two equations with two variables. From equation 1, We can isolate a by saying a equals 14 minus b. Substitute this into equation 2. This gives us the quantity 14 minus b squared plus b squared equals 120. Expanding this, we get 196 minus 28b plus 2b squared equals 120. This simplifies to a quadratic equation. Dividing by 2, we have b squared minus 14b plus 38 equals 0. Using the quadratic formula, we find two possible values for b, count 11.24 and 2.76. Since the question states that a is greater than b, we must choose the smaller value for b. So b is approximately 2.76. However, the dataset was of integers. This indicates there might have been a rounding error in the given variance or the original data points. A quick check. If the standard deviation was exactly 5.2, the variance would be 27.04. The question states population variance is 3.2, which must be a typo. Let's assume the population variance was 27.04 instead. Recalculating with the correct variance of 27.04, our quadratic becomes b squared minus 14b plus 36 equals 0. The solutions are b equals 11.0 and b equals 3.0. These are integers, so this seems correct. Let's look at the original source problem, exercise 13J, question 11. Here, it states mean is 6 and variance is 3.2. Let's work with those exact numbers. Our first equation remains the same, a plus b equals 14. Our variance equation, based on 3.2, is a squared plus b squared equals 120. The quadratic we found, b squared minus 14b plus 38 equals 0, is correct for these numbers. As we saw, this does not yield integer solutions. This is a good learning point. Sometimes, IB questions contain typos. If you solve it meticulously and don't get a clean answer, it's worth double-checking the source. Let's assume, for the sake of getting an integer answer, that the problem intended for a and b to be 11 and 3. If we assume a equals 11 and b equals 3, then a plus b equals 14, which is correct for the mean. And a squared plus b squared is 11 squared plus 3 squared, which is 121 plus 9, equaling 130. If the sum of x squared is 272 plus 130, which is 402, then the variance is 40.2 minus 36, which is 4.2. This does not match the given variance of 3.2. As you can see, the values do not align perfectly with the question. This is a rare occurrence. The key is to follow the method we outlined. Use the mean to find a sum. Use the variance to find a sum of squares and solve the resulting system of equations. Let's work through one more IB-style problem, involving another common technique, finding unknown data values. We have 8 integers with a given mean of 5 and population variance of 5.25. We need to find the values of p and q. Again, we start with the mean. The sum of the integers divided by 8 must equal 5. First, sum the known values. The sum is 25, so 25 plus p plus q divided by 8 equals 5. Solving this gives our first equation, p plus q equals 15. Now for the variance. The variance, 5.2, equals the sum of x squared over t minus 5 squared. The sum of the squares of the known values is 101. So the equation becomes 5.25 equals 101 plus p squared plus q squared over 8 minus 25. Solving this, we find that p squared plus q squared equals 243. Our system of equations is p plus q equals 15 and p squared plus q squared equals 117. From the first equation, p equals 15 minus q. Substituting into the second gives us a quadratic for q. Expanding and rearranging, we get q squared minus 15q plus 54 equals 0. This quadratic factors nicely into q minus 6 times q minus 9 equals 0. The solutions are q equals 6, or q equals 9. We are given that p is less than q. If q equals 6, then p must be 15 minus 6, which is 9. This contradicts p less than q, so this solution is not valid. Therefore, q must be 9. Then p is 15 minus 9, which is 6. This satisfies the condition p less than q. Our answers are p equals 6 and q equals 9. Let's work through a final example that touches on data collection and statistical validity. This is an excellent problem for IBA-AIHL because it requires you to think critically, not just calculate. Brianna and Jess conduct a survey in their class to investigate how many children are in a family. Brianna asks every student, including herself and Jess, for the total number of children in their family. Her result for Jess's family, for example, would be the number of siblings Jess has, plus 1 for Jess herself. Jess also asks every student how many siblings or step-siblings they have. Her result for herself is the number of siblings she has, not the total number of children in her family. The question asks, how will their results compare in terms of mean and standard deviation, and to explain why? Let's first think about the data itself. Each student in the class is in a family. The number of siblings a student has is 1 less than the total number of children in their family. So for every student in the class, Jess's data value is exactly 1 less than Brianna's data value for that same student. Now let's apply our knowledge of data transformations. Jess's dataset is essentially Brianna's dataset, with the constant 1 subtracted from every value. This is a transformation of the form xi maps to xi minus k, where k equals 1. Now let's compare the means. Since a constant 1 is subtracted from every data value, the mean of the new dataset should be 1 less than the mean of the old dataset. So the mean of Jess's data will be 1 less than the mean of Brianna's data. And what about the standard deviation? Remember the rule we discussed. Subtracting a constant from every data value does not affect the spread of the data. The distances between the points remain unchanged. Therefore, the standard deviation of Jess's data will be exactly the same as the standard deviation of Brianna's data. So, in summary, the mean of Jess's results will be lower because she excluded the student themselves from the count. But the standard deviation will be the same because the variability within the family sizes has not changed. The entire dataset has simply shifted down by 1. This problem demonstrates that a deep understanding of the concepts is more important than just memorizing formulas for the IB Mathematics AIHL course. You need to be able to reason about data and its properties. Let's work through one more example that involves 2 steps. We'll be working with a dataset given by a cumulative frequency graph. This graph shows the travel times for 200 students. Our goal is to use the graph to complete a frequency table, and then find the estimated mean and standard deviation from that table. First, let's complete the frequency table using the graph. The first interval is 5 to less than 10 minutes. From the graph, we can see that for t equals 5, the cumulative frequency is 5. And for t equals 10, the cumulative frequency is 30. The frequency for this interval is the difference. 30 minus 5 equals 25. We repeat this process for each interval by taking the difference between consecutive cumulative frequencies on the graph. For the next interval, 10 to less than 15, the frequency is 75 minus 30, which is 45, and so on for all the intervals. We should check that our total frequency sums to 200. Now we have our grouped frequency table. We need to find the estimated mean and standard deviation. We do this by calculating the mid-interval value for each class. The midpoint for 0 to 5 is 2.5, for 5 to 10, it's 7.5, and so on. We can now use a graphics calculator to find the mean and standard deviation from this frequency table. Enter the midpoints into L1 and the frequencies into L2. Running one var stats with L1 as the list and L2 as the frec list gives us an estimated mean of 17.5 minutes and an estimated population standard deviation of about 8.24 minutes. We've covered a lot of ground today. Let's recap the key learning points. First, we learned how to calculate variance and standard deviation for both populations and samples. We saw the crucial difference in the denominator, n for a population and n-1 for a sample to ensure an unbiased estimate. We also learned the specific convention for IB analysis and approaches HL, where you use the population standard deviation, sigma x, unless the question clearly asks for a sample standard deviation. Second, we practiced calculating these measures for frequency tables and grouped data, which involved using mid-interval values. Third, we investigated the powerful rules of data transformation, showing how adding a constant affects only the mean, and how multiplying by a constant affects both the mean and the standard deviation. Fourth, we proved the computational formula for variance, an important skill for the HL course, and used it to solve problems. And finally, we practiced analyzing and comparing datasets, demonstrating how to use the mean to assess the center and the standard deviation or IQR to assess spread. Variance and standard deviation are indispensable tools in statistics. Mastering them is key to your success in IB Mathematics AIHL. Remember, practice is essential. Now it's your turn. Here are 5 IB-style practice questions. I recommend pausing the video after each question, attempting to solve it yourself, and then watching the worked solution to check your understanding. Pause here and give it a try. Use your calculator for efficiency. And here is the solution. First, we find the mean by summing the 8 ages and dividing by 8, which gives us 24.25 years. Next, we calculate the standard deviation using the population formula. The sum of the squared deviations is 63.5, and dividing by 8 gives the variance of 7.9375. The standard deviation is the square root of the variance, approximately 2.82 years. Here is practice question number 2. This is a great conceptual problem about how transformations affect statistics. Pause the video here and try it out. Here is the solution. Each team member is 4 years older, so the data has been transformed by adding a constant of 4 to each value. According to our transformation rules, the new mean is the old mean plus 4. So 24.25 plus 4 equals 28.25 years. The standard deviation, however, is a measure of spread. Adding a constant to every value shifts the entire distribution, but doesn't change the spread or variability between the ages. The difference between the oldest and youngest player, for example, remains the same. Therefore, the standard deviation remains 2.82 years. Practice question number 3 involves finding the mean and standard deviation from a frequency table. Pause the video here and try to find the mean and standard deviation. Here is the solution. The first step is always to organize the data into a frequency table. Now we can find the mean. We calculate the sum of x times f, which is 42. We divide this by the total frequency, 26, to get a mean of approximately 1.62 pets. For the standard deviation, we use the formula with the frequency. The sum of the squared deviations times frequency is approximately 76.53. Dividing by 26 gives a variance of about 2.94. Taking the square root, we get a standard deviation of approximately 1.71 pets. Practice question number 4. This is an excellent problem for comparing 2 datasets with the same mean but different standard deviations. Pause here and try to compare the 2 teams. Here is the solution. First, let's confirm the means and ranges are the same. Both datasets sum to 57 and have 10 values, so their mean is 5.7 runs. Both have a minimum of 0 and a maximum of 12, so their range is 12 runs. They both have the same mean and range. So just looking at the mean and range gives us no way to differentiate the 2 teams. This is where standard deviation becomes crucial. Calculating the population standard deviation, we find that the Rockets have a standard deviation of about 3.9 runs, while the Bullets have a standard deviation of about 3.0 runs. The Rockets' standard deviation is higher. This means their scores are more spread out and less consistent than the Bullets. We can confirm this by looking at the data. The Rockets scored 2 zeros and an 11, while the Bullets' scores are more clustered. This leads to our conclusion for Part C. The standard deviation is a better indicator of variability than the range. It uses all data points in its calculation and is sensitive to how the data is distributed, not just the 2 extreme values. It provides a more comprehensive and reliable picture of spread. Here is our 5th and final practice question. This problem requires you to analyze 2 different ways to measure a variable and compare the resulting statistics. Pause the video and work through this problem, making sure to find both population and sample standard deviations. Here is the solution. The easiest way to solve this is to use a graphics calculator. For sample 1, the mean is 14.6 minutes. The population standard deviation, SX, is approximately 3.73 minutes. The sample standard deviation, S, is approximately 3.93 minutes. For sample 2, the mean is 13.5 minutes. The population standard deviation, SX, is approximately 3.65 minutes. The sample standard deviation, SX, is approximately 3.84 minutes. So for both samples, the sample standard deviation, SX, is larger than the population standard deviation, S. This difference arises because of the denominators in the formulae. Sx uses n1, a smaller denominator, while Sx uses n. This makes Sx larger. The reason for this, as we discussed, is that the sample standard deviation is designed to be an unbiased estimate of the population's true standard deviation. A sample, especially a small one, is likely to underestimate the variability of the entire population. Dividing by n1 instead of n helps correct this bias and provides a more accurate and usually larger estimate. Thank you for watching this detailed lesson on variance and standard deviation. We at DAR Tutors are committed to providing expert tuition to help you master challenging concepts and achieve your academic goals. If you're looking for personalized expert tuition in IB, A-Level, or IGCSE curricula, please don't hesitate to contact DAR Tutors. Our experienced educators are here to provide the support and guidance you need for success. Remember to practice these concepts regularly. The more you work with them, the more confident and proficient you'll become. Good luck.